to discuss about Newton's laws of motion, and also we are going to discuss about dynamics. Okay, so let's talk about first dynamics. Let's define dynamics. Dynamics is a branch of mechanics. It is also a study of the causes of motion, unlike in our kinematics, wherein we simply describe how the objects move. Like we use velocity, we use acceleration, distance, and displacement. But this time, we will look into the different forces acting on the object. So that is dynamics. And also, we are going to describe why objects move that way or why objects stop from moving. So we are going to explain the motion of the object by using the concept of force. Okay. Take note that Newton's laws of motion have certain limitations. For example, in this animation, you can see that this is photon, or we are considering here light. Now, Newton's laws of motion could not be applied when objects are moving at the speed of light or if they are approaching the speed of light. Okay, so that is one of the limitations of Newton's laws of motion. Another limitation is that when objects are very, very small. So when we talk about quantum physics, Newton's laws of motion could no longer be applicable. Okay? So again, Newton's laws of motion have certain range of validity. As long as the object is not moving at the speed of light or is not approaching the speed of light, and objects are not very small up to the atomic level. Now, let's talk about dynamics during the time of Aristotle. So, how did Aristotle explain motion of objects? Aristotle considered four elements that we have: fire, air, water, and earth. Then, for example, you drop a pebble, it will go to the earth or it will move downwards because it belongs to the element earth. For example, you have a feather and then it floats. Then according to Aristotle, the feather floats because it belongs to the air. That's how Aristotle explained dynamics before, without looking into the forces acting on the object. The explanation lies on the different elements. Okay, we also have Jan Buridan, wherein Jan Buridan, according to him, when impetus diminishes, motion also diminishes. And then when impetus is removed, motion will stop or the object will stop from moving. For example, you have an object and then you try to move the object. Then when that impetus or the force, you stop exerting the force, then automatically the object will stop from moving. That's how John Buridan explained motion before. Of course, we also have Galileo Galilei, who is famous for his experiment in the Tower of Pisa. So this is about free fall. According to Galileo Galilei, even though you have a massive object and an object which has less mass, when you drop it, they will fall at the same rate because the force acting on it is gravitational force. Okay, Galileo Galilei showed that bodies were accelerated by gravity to an extent which was independent of their mass, and argued also that objects retain their velocity unless acted upon by a force, for example, friction. Kanina, we have John Buridan. According to him, pag nag-stop na kayo ng force, you're no longer exerting force, therefore the object will stop. But according to Galileo Galilei, even though you're no longer exerting a force, but there's no opposing force, the object will continue moving. But if there is an opposing force, just like friction, therefore the object will stop. Then we also have, of course, we have Isaac Newton. Now let's take a look at the history of the discovery of Newton's laws of motion. When you have to work from home and end up discovering gravity, that is Isaac Newton. So Isaac Newton also experienced the quarantine period. So there was no schooling in 1665. Isaac Newton had to work from home when the University of Cambridge closed because of the bubonic plague. But he was able to discover a lot about mechanics, calculus, optics, and gravity. Okay? So see how productive Isaac Newton was during the bubonic plague or during the pandemic in 1665. Okay? hopefully we will also be productive during this time. And he also recognized the works of the scientists or the physicists before him. With this quotation, I have seen further than others. It is by standing upon the shoulders of giants. And who are those? We have, of course, Aristotle, Galileo Galilei, John Buridan. Okay, so now let's talk about force. How do we define force? What is force? Our elementary definition of force is, of course, simply a push or a pull. But we can also describe it as a quantitative description of the interaction between two objects. Okay, so that is a force. For example, do you think there's a force exerted? Let's say you're sitting beside somebody. Do you think you're exerting a force on him or her? Okay, there is still a force, and that is all actually known as the gravitational force. Because if you have gravitational force, as long as the two objects have masses and they are separated at a particular distance, then there is gravitational force. So they are still interacting. However, that gravitational force is very, very small. Okay, a force is also defined as a net force, or a net force is a physical quantity that is capable of changing an object's state of rest or state of motion. So for example, an object is at rest, and then you exerted a force on it, then suddenly it moved, it accelerated. So you're changing the state of rest of the object. But for example, the object is already moving, and then there's friction. Then eventually the object will stop. So that is changing the state of motion of the object. Okay, so after defining force, let's also talk about the different types of force. Okay, we have what we call contact forces. These are forces resulting from physical contact between objects involved. So kailangan merong physical contact for them to be able to exert force. So here we have applied force. Halimbawa, magtutulak ka ng object, that's an applied force. Normal force. For example, you're standing, and then on the surface also exerts a force on you. There's a gravitational force acting on you downward, and then the surface or the floor where you are standing or where you are standing on also exerts a force on you that is a normal force. And that normal force is always perpendicular to the surface. Okay, we will also derive equations for the normal force. And then we also have frictional force or friction, which acts on rubbing surfaces. So there should be physical contact for a friction force to be able to exert or interact with an object. Then we have also a spring force. We also have a spring force that is also a contact force. Okay, another type of force is the non-contact forces. So it results even when another example of force would be the non-contact forces, result even when the two interacting objects are not in physical contact with one another. So here are examples of non-contact forces. We have gravitational force. For example, you jump. There's no contact between the earth and you, pero the gravitational force is still exerted on you. So that is a non-contact force. Also, electrical force. We have electrons and protons. They are exerting force on one another, even though they are separated by a certain distance. And same with magnetic forces. If you have two magnets, let's say face ang north, then south pole, there will be a force of attraction even though they are separated. Then, of course, we also have the nuclear forces inside the atom. When we say net force, we are talking about the sum of all the forces acting on the object. Let me show you some examples of very simple calculations of net force. You have here a physics book. Then there's a normal force acting on it upward, that's 20 newtons. And then there is also a gravitational force, 20 newtons downward. So the net force here is equal to 0. Then looking at this illustration, you have a physics book again. Along the y, the net force is equal to 0. Along the y, the net force is equal to 0. But when you look at along the x, you can see here that there is a net force 5 newtons to the left. Okay, let's take a look at these examples. We have 1,200 newtons upward, then you have 800 newtons downward. What is the net force there? that is 400 newtons, and then the direction is upward. Then you also have the force exerted air resistance by air, and then the gravitational force 800 newtons. So the net force in this example would be 200 newtons downward. Then another example, you have the net force is 20 newtons to the left. Here are other examples. We have 5 plus 5, we have 10 newtons, 5 minus 5, so we have equal forces, however, they are exerted at an opposite direction, so you have 0. Net force is equal to 0. 5 newtons plus 10, you have 15 newtons. Okay, I'll give you more examples on solving for the net force, wherein we will also be using trigonometric functions, the sine, cosine, and tangent. Then frictional force, again, it's a contact force. It acts on two bodies or on surfaces of two bodies. And also it is a force which always opposes the motion of the object. And the component is always parallel to the surface. Take note of that. Friction is always parallel to the surface. Yung normal force naman kanina is always perpendicular to the surface.
Okay, so looking at the book also, the man is exerting a force on it, and then he stops exerting a force, then the force acting on the object is now friction. Since there's friction, therefore the object will stop moving because of frictional force opposing the motion of the object. What if, let's turn off friction. What if there's no friction? I want you to observe what happens to the book. The man is no longer exerting force. Okay, the man is no longer exerting force. However, the book continues to move at a constant velocity because there is no friction. Okay. The next example. Okay, same with this. So you have here a dog again. There's no friction. There was an initial force exerted on the dog. Therefore, it now will continue to move. Okay, what if there's friction force acting on this one? Yeah, you have here a cabinet. Then there's an applied force. That's the total force exerted. And then, of course, you have frictional force. So as I have mentioned, since there's friction, it will stop from moving. Okay, now let's take a look at the graph. So again, you have the applied force, then you have the total force, but there's a friction force acting on the object. Yeah. So you can see here in the graph, okay, so you can see here in the graph that static friction or the friction acting on the object before it moves is actually higher. So makikita nyo yan doon sa may parang may well in the graph. Okay, that's around, malapit siya sa negative 640 newtons. So that is static friction. When the object is initially at rest, that's the friction acting on the object. But when it starts to move, the friction is less than, it's around mga 350, negative 350 newtons when it's already moving. That is kinetic friction. So those are the different types of friction. We have static friction and kinetic friction. Okay, what's the definition of that? Static friction is the friction acting on the object which is still at rest. And then kinetic friction is the friction acting on the object which is moving. Take note again that kinetic friction is always less than the static friction. We also have under kinetic friction, rolling friction. So for object which rolls, so they also have this rolling friction acting on them.
Then we have different kinds of friction. Yun nga, as I have mentioned, we have static friction, we have kinetic friction, and we also have rolling friction. Kinetic friction is always higher than static friction. Friction also depends on the following. We have the kind of surfaces. Syempre, the more rough the surface is, the greater is the friction. The mass of the object. The greater the mass of the object, the greater is the friction. What about the velocity of the object? But when you are biking and then you are trying to move at a faster rate, you can observe that the air resistance, you will feel more air resistance. So the velocity also affects the air resistance. It will be higher as the velocity increases. And then you also have the area of contact. Of course, the greater the area of contact, the greater is the frictional force. Dahil mas greater yung area which are rubbing, or mas greater yung area of the rubbing surfaces. Then we have an equation, F, para ano yan? Physics is fun. F equals mu n, wherein mu is the coefficient of either static friction or kinetic friction, and n is the normal force. Again, we will derive in the calculation normal force. So we have, again, F is friction, mu is the coefficient of friction, and then n is the normal force of the object. Friction should also be in newtons. If we are going to express normal force, should be in newtons. Therefore, the coefficient of friction is unitless. Let's think about this. Why do we move backwards when a driver suddenly steps on the accelerator? And why are seatbelts important? So those are some applications of Newton's laws of motion. So, Isaac Newton will help us answer those questions. Law of inertia is the answer. Ano nga bang inertia? Okay, when we say first law of motion, that's the law of inertia. A body at rest tends to remain at rest. A body in motion keeps on moving at a constant velocity unless acted upon by a net external force. So that is Newton's law of inertia. But how do we define inertia? Inertia is the property of a body which resists any change in its state of rest or state of motion. So inertia has something to do with resistance to the change in motion or to the change of state of rest. And this is also proportional to mass. For example, may mas mataba, tapos may mas mapayat, and then somebody is trying to push them. Mas mahirap itulak yung mas mabigat because he or she has greater resistance or has greater inertia. So that is law of inertia. Okay, halimbawa sa jeep naman. Okay, pag-isipan nyo to. It's initially moving. So, nagmo-move na. And then you also observe that when you are initially moving and then the jeep suddenly stops, of course, magmo-move kayo. Diba? Papunta doon sa driver pag biglang nag-stop. Now, who will be thrown farther? Let's say, mayroong mas magaan na passenger and then you have a heavier, there are two passengers, let's say a heavier and a lighter one. And then they are initially moving, then the jeep suddenly stops. Who will be thrown farther forward and why? Okay? For me to be able to check if you're watching the video, I want you to leave your answer in the comments in our group or in the comments in the YouTube. Okay? So I will wait for your answer and then we will try to explain this during our asynchronous meeting. Okay, two passengers of different weights are in a moving jeep. And I want you to think about this. Ito yung question kanina. Okay, I want you to think about this. Two passengers of different weights are in a moving jeep. Then suddenly the jeep stops. Who will be thrown farther? The heavier or the lighter passenger? And why? Okay, seatbelts are very important. Why? As we have mentioned, objects have this inertia. Okay, they resist the change of state of rest or state of motion. If you are initially moving, the tendency is to continue moving. That's why we are moving forward. When suddenly, the driver steps on the brake. So, bigla kayo mag-move forward. Bigla mag-move forward because we are trying to resist yung change ng motion. That's why we are still going with the flow of the jeep. But why are seatbelts important? Seatbelt this time will provide the force needed so that you will stop from moving. Okay? So there is now an external force acting on you so that you will stop. Because if there's no friction, let's say there's no friction, there's no seatbelt, and then you will continue to move at a constant velocity. Okay? So seatbelts are very important so that you will not continue to move forward. Okay. This is another animation on that. Sana lahat tayo, we are very skilled that we can do that. And again, we have a tendency to move forward or to continue to move. Another example is this. So you can see there that the ladder is not tied. There's no force, external force acting on it. Therefore, it will continue to move forward.
Okay, one application of Newton's first law of motion is the first condition of equilibrium. So you can see here in the figure, okay, I want you to look at the illustration. You have the normal force, which is pointing upwards, and then you have the gravitational force. So the normal force is equal to the gravitational force. Therefore, when we sum up the forces, that's equivalent to 0. Okay? So the net force acting on this is 0, and the body is at rest. If an object is in the first condition of equilibrium, the body is either at rest or it's moving at a constant velocity. If the net force or the summation of forces acting on it is equal to 0. Okay, so I want you to take a look at the animation. So for example, you have here. Okay, for example, you have here the crate, and then let's try to apply a force on this until it moves. So let's have this one. Okay, so I want you to observe the motion of the crate. What if I add another mass? So let's reset it. I have applied 250 newtons. So let's have a crate again. Okay, what if this time we have a crate and then we have a girl? Then let's apply 250 newtons again. So you can see that this time the crate is moving at a slower rate. Therefore, the acceleration is inversely proportional to the mass. So what if we just change the force? So let's remove this one. And then let's just apply a force here. That is, okay, here, this amount of force. And then what if we increase the force? Yeah, so you can see how the object moves or how the object accelerates. The higher the force, you can see here in the animation that the higher the force, the greater is the acceleration of the object. But the higher is the mass, the lesser is its acceleration. So that is Newton's second law of motion. Acceleration is directly proportional to the force, but inversely proportional to the mass of the object. For the Newton's second law of motion, it tells us that the acceleration of the body is proportional to the resultant force and inversely proportional to the mass of the object. The acceleration also is in the same direction as the net force acting on the object. So we have here the famous equation F equals ma, or if you are going to derive an equation for acceleration, acceleration is equal to the force divided by the mass, where F is the resultant force or the net force, m is the mass, and a is acceleration due to gravity. So that we will have a unit of Newton for force, the mass should be in kilogram, and acceleration, we have meter per second squared. Okay, do you know that the mass is not the same as the weight? What's the difference? Okay, anyone? If, for example, you're on Earth, then you're sent to the moon. Okay, your mass will be the same. So the quantity of matter is the same. But if we are going to talk about weight, it will be different. On Earth, you will weigh or you will be heavier in terms of your weight. Unlike when you are on the moon, you will be lighter. It is because the gravitational acceleration on the moon is of course less than the gravitational acceleration on the Earth. Okay? So let's define again. Mass is the quantity of matter in an object and it's a measure of inertia, while weight naman is the force upon an object due to gravity. So if you are on Earth, mg, wherein that's your mass, times the acceleration due to gravity of 9.8 meters per second squared. Okay. So F equals mg, that's our weight. Okay, it's different from the mass. Okay, I want you to analyze this one. We have here, this is free fall. We have mentioned that acceleration is directly proportional to the force However, it's inversely proportional to the mass. But looking at this, in free fall, they will accelerate at the same time. Why? Why will the elephant and the pebble accelerate at the same rates even though they have different masses? Because according to Newton's second law of motion, acceleration is directly proportional to the force but inversely proportional to the mass. Okay, let's check why. Take note also that the force acting on the object is equal to mg. So that's the mass times the acceleration due to gravity. And then, it's inversely proportional to the mass. However, let's go back on this. The gravitational force exerted on the elephant is higher, but the gravitational force exerted on the pebble is lower. Therefore, that weight or that gravitational force is compensated also by the mass, so they can have the same acceleration. So let's take a look at this. And for example, for the boulder, okay, it has bigger weight, therefore it has bigger force exerted on it. Then it also has bigger mass. But for the pebble, you only have a very, very small gravitational force. So just a small f divided by a small m. So that is possible that they will have the same acceleration. So you see that Newton's law or Newton's second law is still applicable, okay? But looking at this animation, you can now see here that there is already a force exerted by air resistance. So initially, the gravitational force is 1,000 newtons, yan. Then there is now air resistance, which is increasing until the acceleration will become 0. This is now at the first condition of equilibrium wherein the net force is equal to 0 and the object will continue to move at a constant velocity. So this is a very simple computation of net force. So you have there, initially gravitational force is the only force acting. So that's 833 newtons. And then you already have the air resistance, 350 newtons. And then air resistance increases, 700 newtons, until the force exerted by the air, until air resistance is equivalent to 833 newtons, same as the gravitational force, 833 newtons. So again, net force is equal to 0 and the object will continue to move at a constant velocity. Hindi siya biglang mag-stop sa air. It will just continue to move. However, this time it's moving at a constant velocity. It's no longer accelerating.